A liquid is kept in a cylindrical vessel which is being rotated about the vertical axis through the center of circular base. The radius of vessel is r and the angular velocity of rotation is omega. Then the difference in the height of liquid at the center of vessel and the edge is. Before solving the question, let's understand the relation between the pressure along the radius when a vessel is under rotation. Now, if I consider a vessel with fluid is rotating about its own axis with angular velocity omega at a radius r from the axis, if I am considering a thin layer of fluid with thickness dr and height h. Now, pressure inside the surface of fluid, taking it as P, pressure outside surface of fluid, taking it as P plus dP, where dP is the negligible pressure difference. Since fluid is in rotational motion, there must be a centripetal force acting on the fluid radially inward, which I am considering it as F. Then F should be equal to dm omega square r, where dm is the mass of the thin layer of fluid. Then force F I can write as pressure difference dP into surface area 2 pi r h is equal to dm omega square r. Now if I multiply both sides with thickness of fluid dr, then this will be dP into 2 pi r h dr is equal to dm omega square r dr. Then I can write this as dP by dr is equal to dm omega square r by 2 pi r h dr is nothing but the volume of the fluid, then that will be dV. Then I can write dP by dr equal to rho omega square r. Now we are going to use this relation in the following question. When vessel containing fluid is under rotational motion about its own axis, then surface of the fluid will be upward concave surface. I am taking center of surface of fluid is point A at the same radial reference level near the surface of container, taking it as point B, and the surface of fluid above point B, considering it as C. Now the height difference between the point C and B, considering it as h. Then pressure difference between point B and C I can write as PB minus PC equal to rho g h. Now pressure difference between point A and B I can get from the relation dP by dr is rho omega square r. Then I can write dP equal to rho omega square r dr, where I am integrating dP from point A to P and r from center of the cylinder to the boundary of cylinder cap small r. Then PB minus PA is equal to rho omega square r square by 2. Since point A and C are the surface of fluids, then pressure at point A and C must be atmospheric pressure. Then I can write PA is equal to PC, which is equal to P naught. From the pressure relation between point B and C, we can write PB equal to rho GH plus P naught. Consider this is equation 1. And from the pressure relation between point B and A, we can write PB is equal to rho omega square r square by 2 plus P naught. Consider this as equation 2. Now by equating equation 1 and 2, we will end up with rho GH is equal to rho omega square r square 2. Then height h is equal to omega square r square by 2g. So the right answer for the given question is option 2.